Right, this is the next section, air and water. So there's a basic overview of the composition of air. Clearly, the majority of what we breathe is nitrogen, 78% of it, about. Oxygen, the green, is 21%. And then you've got argon, which is the most abundant of the noble gases, and then other noble gases. Carbon dioxide, which obviously is a big problem as this grey chunk is increasing, and water vapor and solids or particulates, as they're often called. Very small percentage, but these things affect us greatly. Okay, you need to have an overall idea of the composition of air. So we talk about 78% nitrogen, 21% oxygen, and then about 1% of the other things. And remember what the other things are, essentially. You won't be asked exact figures on the other things. The fractional distillation of liquid air. Quite amazingly, we can cool air to the extent that its components liquefy. So what we've got to do, essentially in the first stage, we have to get that temperature right down to minus 200 degrees C. And then we slowly let the liquid air warm up so that we can fractionally distill its components. If you remember back to year 10, fractional distillation was the separation technique used for separating liquids that were miscible. So if I've got liquid air, I've got all of the components in liquid air, then if I slowly warm the air, the more volatile gases will come off the top, in this case nitrogen is indicated, and the less volatile will stay at the bottom. If we keep the temperature low enough, we can take this liquid oxygen off, and we know that oxygen is very useful, so I'm sure we'll find lots of uses for it. So the process essentially is this: you take the air in, there's a first step where you have to remove dust, carbon dioxide and water. Why do you think you have to remove those things? Well, essentially, all of these things potentially can block up the system. They can block the pipes in the system. So dust will accumulate and block pipes, but carbon dioxide and water, they're gases and a liquid in water vapor when they're taken in, but as soon as the temperature gets down to 0 degrees or 273 Kelvin, the water will freeze and that will block the pipes, a little bit like the pipes that get blocked in the winter. It will freeze and potentially burst the pipes. And carbon dioxide freezes at about minus 56, I think, minus 56 degrees Celsius. And that also would cause the same problem. It would block the pipes. So write your explanation in there. We take the air in, we slowly compress it. Now you'll know from pumping up bicycle tires that the pump gets hot, and it's not just because of the friction. If you compress a gas, you heat the gas up. Okay? So we slowly compress it, and then it warms up. Then we cool it with liquid nitrogen. So we cool it with something that's very, very cold. And then we pass the gas through these pipes, and then we allow it to expand suddenly. So if compressing a gas warms it up, allowing a gas to expand cools it down. So if we do that, the gas turns to liquid, the air turns to liquid. And then if it's at minus 200 degrees, we put it into the fractionating column and we can separate the major components. Now, this expansion of gas causing a cooling effect, you see that every day. You feel it every day when you put on deodorant. And deodorant comes from a pressurized can, And when you squirt it onto yourself, you can feel the cold. And that's because the gas is expanding suddenly. Okay. And then once we've got the components, then we use them in lots of different contexts. So you have to remember some of these uses. Oxygen, for example, is used to help animals, humans, dogs, animals, to help them breathe. Okay? Also, we go diving. We go scuba diving. So oxygen is one of the, it's a major component of the tanks, isn't it? They put other things in the tanks too. We can use oxygen for cutting steel, for example. Oxyacetylene torches will cut through steel. So we use pure oxygen to get the temperature of the flame really high. Nitrogen, well, nitrogen, a modern use is to remove blemishes, some kind of growth on skin. So it kills the growth on the skin, it causes it to freeze, and it doesn't cause too much damage to the surrounding cells. And also we use it to cool things in lots of different contexts. Liquid nitrogen is a very good cooling agent. They even use it to make ice cream nowadays, I think. And the noble gases, well, we've talked about their uses before. There's one use, which is the production of light if you apply an electric field to them. But there are other uses, aren't there? You can look back at that. Right. Essential chemistry, have a read through those pages and try the questions. Okay. Pollution. Now, pollution is something we all need to worry about because our activities, human activities, cause a tremendous effect on the environment. This is an article you can read through, but it's amazing how we've all become used to bad air. Air that is polluted contains some of these components. So it's something to be aware of. You see it every day when you're in a traffic jam. You see the smoke and the fumes coming out of cars and buses, and that must have an effect. It has an effect on the environment. It has an effect on life, on us. So the main pollutants in the Earth's atmosphere are listed here. We're going to go through them one by one and have a chat about them. Here's a carbon dioxide. Now, technically, carbon dioxide is not a pollutant as it's always existed in the atmosphere and it's produced by natural processes. I mean, one of the processes, obviously, that we do too much of is we combust fossil fuels. So when fossil fuels are burned, if they're burnt with lots of oxygen, then we produce carbon dioxide, the complete combustion of fossil fuels. All fuels that contain carbon. By respiration, carbon dioxide is produced. So when plants and animals respire, carbon dioxide is produced. And when acids react with carbonates, you could get acids in the atmosphere reacting with minerals, or the thermal decomposition of limestone, which we use in the process of making cement. Thermal decomposition of limestone, you will remember, produces lots of carbon dioxide. Okay, so carbon dioxide, these are its sources. You need to remember the sources of it. Complete combustion of fossil fuels is the major one at the moment, isn't it? So, complete combustion of methane. So this one I've done for you. And remember, when you have complete combustion, you've got plenty of oxygen, and the two products are carbon dioxide and water. The water will appear as water vapor at first because this reaction produces lots of heat, and then it will condense to form droplets of water. Okay, so there's the balancing for you. It's good balance in practice, complete combustion. Let's have a go with a more difficult molecule, petrol, which is mainly C8H18. So this is where you can have a go at the equation. the complete combustion of petrol. Remember, you're reacting it with oxygen, and the two products are carbon dioxide and water. Have a go. Right, there's the balancing. We try to avoid using fractions in equations. This could have been 1, 12.5, 8, 9, but we've doubled it to have whole numbers. It says plus energy, but really that should be delta H is negative. The enthalpy change or the energy change is negative. It's an exothermic process, isn't it? It's an exothermic process. These are fuels, and by definition, fuels produce energy. The gas carbon dioxide is considered to be the main culprit of global warming. It is a greenhouse gas. It's not the best greenhouse gas, but it's the one that has the most effect, simply because of its quantity. There is just lots and lots of carbon dioxide. Other greenhouse gases of note are methane and water vapor. So, methane and water vapor, we've got to think about where they come from too at some point. So we'll discuss that in a little while. But let's worry about what the greenhouse effect is. Now, electromagnetic radiation comes from the sun. The part of the spectrum that's responsible for heating things is called the infrared spectrum. Okay, it's just below the visible spectrum in wavelength. I say it's just below. The wavelengths are slightly longer than the visible spectrum. So it comes in, it warms up the particles in the Earth's atmosphere, and instead of just bouncing straight back out, these particles then re-emit infrared, but at a slightly longer wavelength, which finds it hard to escape, so much of it is kept in the atmosphere. So you get this warming effect. This is something we've all experienced in a greenhouse or a conservatory or a place with lots of windows, that the infrared, the energy gets through the windows, something happens and it causes the wavelength of the infrared to increase, the energy is less, so it finds it harder to escape. So there's an overall input of energy to the space. Okay? So that's more or less explained there. You can read back through it. The overall result of the process is that the atmosphere warms up. So we get an increase in temperature. Now that increase in temperature has been very small as an average across the globe, but only a very small increase in temperature has caused very big problems already, and will continue to cause them if we don't start doing something, and rapidly. Methane. The main sources of methane are the digestive systems of farm animals, cows, pigs and sheep. Okay, so the flatulence of farm animals, and also the gases from both ends of these animals cause an enormous amount of methane to be expelled. You can also get methane from the decomposition of vegetation, which you may have experienced walking through a bog or walking through a swamp. When you walk into the mud, bubbles of gas appear through the mud, and that's methane gas. It's decomposition of vegetation, of plants, not so much animals, but mainly plants underneath the surface, that when you stand on it, you disturb the methane and it escapes. Water vapor is caused by evaporation of the rivers and seas. If we increase the average global temperature, obviously more water evaporates, and this causes an increase. There's kind of a spiral effect here, isn't there? A vicious circle, a spiral, whatever you want to call it, but it gets worse and it makes itself worse. Right, carbon monoxide. Now, carbon monoxide is produced when you have a fossil fuel burnt, or a carbon-containing fuel burnt in insufficient oxygen. Okay, so you need to change the products of the combustion reaction, well, one of the products. So for example, we saw methane before, and it was in complete combustion. it produced carbon dioxide and water. But in incomplete combustion, the products are set as carbon monoxide and water. And this is a mistake. That should be a gas, not a solid. So you can change that on your sheets. And then the balancing is slightly different. So you set the products as carbon monoxide and water, and then you balance with as much oxygen you need. Okay. If there's even less oxygen, typically, then the products change again. Water's still made, but in this case, carbon or soot is produced. That black stuff that you get on the inside of chimneys. And because you've changed the products, the balancing changes again. Okay, so complete combustion produces carbon dioxide. Incomplete combustion can produce carbon monoxide and carbon. They're examples of incomplete combustion. Carbon monoxide is a colourless, odourless, deadly gas due to the fact that it bonds with the hemoglobin in the blood, and this causes oxygen starvation. The hemoglobin in the blood prefers carbon monoxide to oxygen, so less oxygen gets to the brain, so essentially you lose consciousness and then pretty quickly you die. Very, very hard to reverse the process too. You need a blood transfusion because the carbon monoxide bonds so strongly to the hemoglobin. Right, just to practice your equation writing, write the 3 equations for the combustion of propane, C3H8. So you want complete combustion to produce carbon dioxide, and you want 2 equations for incomplete combustion to produce carbon monoxide and carbon. Have a go. Okay, check your balancing. Now you can see here they've used fractions, which is okay. It's okay at A level. At IGCSE people prefer whole numbers. But this is good because it means you can compare the amounts of oxygen. So with complete combustion, there's 5 moles of oxygen. With incomplete combustion, if you produce carbon monoxide, 3.5 moles of oxygen. And incomplete combustion to produce soot is just 2 moles of oxygen. So you can see the less oxygen you have, the more incomplete combustion you get. Sulfur dioxide. Fossil fuels contain sulfur. There's sulfur in the earth and it appears in fossil fuels. When it burns, it forms an acidic, pungent gas called sulfur dioxide. An acidic, pungent gas. Now, pungent is when you breathe it in, it gives you a shock. It's a very strong effect. There's the simple equation. Obviously, sulfur is a solid, oxygen a gas, and sulfur dioxide is a gas. This gas then is in the atmosphere. It combines with water in the atmosphere, with rain, and it produces the strong acid, sulfurous acid. Now remember, strong acids are those which completely dissociate, they completely ionize or dissociate in water to produce a high concentration of hydrogen ions. A weak acid, they only partially dissociate, but strong acids, they fully dissociate, or almost fully dissociate. Sulfur dioxide, and then sulfurous acid, is the main cause of acid rain. And it attacks buildings and ecosystems. It changes the pH in rivers. Plants, insects get affected by it. It also irritates the eyes and causes respiratory problems. Now, acid rain has always existed because carbon dioxide dissolves in water to give carbonic acid, and carbonic acid is an acid, but it's a weak acid, so the pH isn't very low. So it's completely normal for the rain to be a little bit acidic due to the carbonic acid. But this sulfurous acid causes the pH to be very low, a pH of 1 or 2. And this causes big problems in ecosystems. Nitrogen oxides typically are formed by the burning of fossil fuels in engines, in high temperature engines. And again, the effects are acid rain, because the nitrogen oxides dissolve in rain, and respiratory problems. Now they're indicated as NOx because there's a different variety of nitrogen oxides that can be formed. So this is like the generic term for nitrogen oxides, NOx. But you can have N2O, NO2, N2O4, NO. So there's a combination of nitrogen oxides. Nasty things. And they're the things that often in cities cause respiratory problems with people. Asthma, for example. Ozone is O3. It's O3. Now, oxygen can form these ozone molecules, but typically they form in the upper atmosphere, in the stratosphere. And because they form in the stratosphere, then they don't really bother us. What they do is they protect the life on Earth because they absorb the high energy radiation from the sun. So ozone in the upper atmosphere is like a kind of factor 50 for the Earth. In lower regions, car engines and combustion engines can form ozone, especially in the summer when temperatures are higher, and that can cause respiratory problems. So sometimes you get ozone warnings. But the classic ozone problem was related to a hole in the ozone that formed over Antarctica. And it's taken quite a long time to start to fix that hole. Now that hole was caused by the widespread use of CFCs, chlorofluorocarbons. They were banned, I think, in the 1980s, and so slowly this hole is being fixed. Okay? But the CFCs destroyed the ozone in the stratosphere, causing more high energy radiation to get to the Earth's surface. It's getting better. You can look at pictures on the internet. You can see the hole is improving. It's getting smaller. The equation, the overall equation for this process, where 2 moles of ozone are destroyed and they make 3 moles of oxygen. That's what happens in the upper atmosphere if you have these CFCs floating around. At ground level, ozone can cause respiratory problems. It's also used nowadays at ground level for sterilization. And it can be used to clean the bacteria and viruses from rooms, and also in water for swimming pools, for example. It kills bacteria. So it is useful. You've got to be careful though, because it is also potentially toxic for the human. That's ozone. And the last thing to discuss, although it's less of a problem than it was, lead used to be used in fuels. And people realized that it was causing tremendous problems in the development of children and also in adults. So lead poisoning is not something that you want to have. The lead compounds, or lead, gets into your system and cannot be excreted. So it accumulates in different parts of your body, especially the brain. There are some parts of the world where there's more lead in water, which causes problems in people. And here's some of the problems it can cause for the human. Brain causes IQ problems, hearing loss, learning disabilities, damage of the kidneys, anemia in the blood, your nervous system can be damaged, and decreased bone and muscle growth. So lead's a really nasty thing. It's something to avoid. Now, it was banned from fuels quite a long time ago, but there are still some old cars and old engines that use leaded petrol. Nowadays we have unleaded petrol. And then particulates, something it's a problem when you're burning lots of fossil fuels, especially incompletely, as we saw before. You can form soot and other particles that can go into the atmosphere as smoke. So these particles can essentially, they can go into the atmosphere and they can affect people, cause respiratory problems. They deposit on the roads and on cars and on balconies. They're up in the atmosphere, but obviously because they're particles of solid, they will settle. You can see the sources of particulates. Some car engines, like diesel engines, produce more particulates, which is why they're considered to be more dangerous, and they're banned from major cities when there's pollution problems. And these particulates can also cause problems with the atmosphere. They can cause fog, strange weather patterns. Okay, that's particulates. Now, we have to think of ways of reducing pollution. So, we have to think about how we can reduce carbon dioxide emissions. So, have more efficient engines, public transport, save energy in the home, and use alternative and sustainable sources of energy. And you've probably researched these before, but things like wind power and solar power, tidal energy, geothermic energy, all of those things, something to think about. Okay, so alternative forms of achieving what we need in terms of energy that don't emit carbon dioxide. And also we've got to make sure we treat any waste liquids or gases in industries so that they don't just go into the atmosphere. Power stations have something called flue gas desulfurization. The sulfur dioxide is reacted with calcium hydroxide or other bases. So for example, look, this is the gas coming from the chimney. There's a spray here. The limestone is used in this case. So somehow they spray limestone in, and it reacts with the acidic gases that come from the chimney, in the waste products of the chimney. And then the reaction causes a formation of salts, which form at the bottom of this. Gypsum's a salt. And we remove the salts. This whole process is to stop acidic gases going into the atmosphere. We need to control lead emissions and lead in petrol. And you can see this is quite an interesting one. This shows the lead in the blood of children between 3 and 12 years in relation to the lead in petrol. So as the lead in petrol went down, almost parallel, the lead in the blood of children went down. Okay, so very, very clearly there was a direct correlation, and that had its negative effects on the development of children. And remove sulfur from fuels before they're burnt. So before you burn them, get the sulfur out so it doesn't cause the production of sulfur dioxide. Another important thing to use is one of these. This is a catalytic converter. It's used in cars and other vehicles, and essentially nasty gases go in. This is the red stuff. You've got hydrogen, that should say hydrocarbons, not hydrogen. Hydrogen doesn't go in. So unburnt hydrocarbons, for example petrol, goes in, and carbon monoxide from the engine, and nitrogen oxides from the engine, look, NOx. They go in. And then you have in here a catalyst. This catalyst, it says down here, is a mixture of different exotic transition elements. And there's some alumina and cerium oxide and basically a big mixture of things. But this is in the form of like a honeycomb kind of gauze catalyst. The gases go shooting in here. They're at quite high temperature. They go through this system of gaps, and then the reactions that happen are, well, the carbon monoxide makes carbon dioxide. The unburnt hydrocarbons, so the oxygen or the fuel, gets turned into carbon dioxide and water. And the nitrogen oxides react with the carbon monoxide to make carbon dioxide and nitrogen. And that all happens in the fraction of a second, in the blink of an eye. So what comes out is just water, carbon dioxide, and nitrogen. This is a catalytic converter. It's a catalyst that changes nasty gases to the less nasty gases. Right, read the pages and answer the questions.